Hi, everyone. So last time we talked about traversing binary trees, and let me remind you what these things are. Right, so we talked about binary trees and traversing them. Um, Let me remind you, we had three types of traversal. So the first was called in-order traversal, and here's how it works. Uh, so the traversal visits all vertices in the tree, and let me tell you what's the order. So first it visits the left subtree. Then it visits the root, and then it visits everything in the right subtree of the root. And in this example, this is what's going on. So first we, recursively visit the left subtree. So we visit this under everything under 5. Then it's 10, and then it's the right subtree. So let's focus only on the left subtree for a second. How do we traverse, do in-order traversal on the left subtree? So it's left, 5, right. Okay, so put something, 5, right. What's on the left? On the left, it's 1, then 5, and then on the right, it's 7. So this gives us the traversal of the left subtree. This is 10, and similarly, this is the traversal of the right subtree, right? So it's left, which is 16, then 21, and then 25. So what's the in-order traversal? It's simply this sequence of the vertices in the tree. So we visit all the vertices, and this is the order that we're getting. Okay, so this was in-order traversal, in order because, root is in the middle. We have pre-order traversal. So pre-order says root comes first, then the left subtree, then the right subtree. So in this example, we visit first 10, then we process the left subtree recursively, and then the right subtree. So to process the left subtree, what will we do? We process 5, then left and right. So what's left of 5? It's 1. What's right of 5? It's 7. So for the left part, we get 5, 1, 7. And for the right part, 21 is the root. 16 and 25 are on the left and on the right. So this is the root, left subtree, right subtree. So the final result will be this 10, and then 5, 1, 7, and then 21, 16, 25. Notice, I would like to emphasize, there's no separation here, which is the root, and where is the left subtree, and where is the right. So just a sequence of all vertices in some order. So this order is called pre-order. And similarly, we have post-order traversal, and it goes as follows. Post order means the root will come last. So first we visit left subtree, then right subtree, then the root. So in this example, we have left subtree, then right subtree, and then the root. So the root is 10, that's easy. What about the left subtree? So it's something, something, 5. Yeah, something, something, 5. What about the right subtree? It's something, something, 21, right? Something, something, 21. Let's look at the left part, only recursion on the left. What's on the, what do we have in the recursion inside 5? So it's 1 on the left, 7 on the right. So the answer is 175. That's processing our left subtree. 16, 25, 21. 16, 25, 21. This is processing right subtree, and then 10. So the final result will be simply this. Okay, so this is 175, this is the left subtree. 16, 25, 21, this is the right subtree. And 10, this is the root. Okay, this is our answer. And let's write code for this. So it's actually not very difficult. It's pretty straightforward. So let's say we get, a pointer to the root. And let's see. So if root is null, then there's nothing to do, which is nothing. If the root is not null, so it's pre-order. So what do? We first print the data. Then we print the left subtree recursively, right? So we don't print the data in the left subtree, rather we recursively apply pre-order traversal on the left subtree and then recursively apply traversal on the right subtree. Okay, that's your algorithm. And let me ask you this question. So what do you need to change in order to get in order and in order to get post order? So this is pre-order, right? So root comes first. Yeah, so it's not very hard to see. For in order, we'll need to change these two lines, like 2.1 and 2.2. So print data will come in the middle. And for post order, print data will be the last line. Right. So yeah, pretty straightforward algorithm. And we'll see code in a second. The code doesn't differ from this by much. And what's the running time of this? So the running time of this is, if n is the number of vertices in the tree, then the running time is linear in n. So basically we process each node exactly once, right? So for each node, we visit the node and then go to the children, right? Go to recursively to the left child, recursively to the right child. So the total running time is order n. Okay, now let's see the code for this. And here's what we'll do for the code. Okay, so this is our one node, right? So an struct node is value pointed to the left child, pointed to the right child, and pointed to the parent. And given this, how will we do, for example, print pre-order? So we get the root. If root is null, just do nothing. Otherwise, print the value at the root, recursively, apply pre-order on the left subtree and apply a pre-order on the right subtree. For in order, exactly the same thing, but we put this print data or print value in the middle. Post order, exactly same thing. Right. So I hope this is clear. I mean, I feel it's pretty straightforward. Okay, let's try to run some code and we'll see what we get. Okay, so let's look at our main function. So we create 7 nodes here, and we create node whose value is 1, 2, 3, 4, 5, 6, 7. And here's what we do. So we set the left child of 1 to be 2, and the right child of 1 to be 3, and the left child of 2 to be 4. So this is the tree that we're getting, right? So the left child of 1 is 2, this one. The right child of 1 is 3, it's this one, and the left child of 2 is 4. Okay, what are we doing next? In this line, we set the right child of 2 to be 5. So this is the tree that we're getting. Okay, so what are we doing next? So we set 6 to be the left child of 3. We go this way. And 7 to be the left child of 6. So it's this one. Right, so let's see some simple printouts. Let's say these ones. If we want the value at the root, we simply print n, the value at n1. And the next line says, so if we go to root to the left and then get the value, so from the root we go left, it prints 2. Because from the root we go left, yeah, that's 2. And what is this one? So the value we take the root and then we go right and then we go left. So take the root, we go right and then go left. It should print 6. Yeah, it prints 6. Okay. And if we take the node 7 and we want to know what's the parent, so the parent of 7 is 6 indeed. Okay, that's pretty straightforward. Right, this is exactly what we expect to happen. Okay, now let's run these two. Okay, so this is our tree, and we would like to run pre-order and in order, starting from 1. So let's see. So pre-order, it says is this. So let's see. Pre-order, we first print 1. Yeah, that's 1. Then what's the left subtree? So the left subtree is 2, 4, 5. 2, 4, 5. And the right tree is 3, 6, 7. Okay, yeah, 3, 6, 7. Hey, hey. We said this is exactly what's supposed to do, or not this one. The pre-order, this is exactly what it's supposed to do, and it seems to be doing it. Well, Yeah, it's nice when code actually works. And for in order, let's see, 1 is the root. So we first print the left subtree, which is 4 to 5. Yeah, says 4 to 5. And then we print 1, and then 7, 6, 3. This is the in order of the right subtree. Okay, so we get exactly what we expected to get. Good. Okay, so this is what we have now. And here is what we're going to do next. Next, we'll do this exercise. So the plan is to do a bunch of practice problems on binary trees, and we'll start with this nice problem. So draw a tree whose pre-order traversal is this sequence and whose in-order traversal is this sequence. Right, so stare at it for a minute, try to think, or maybe pause and try to think. Let me tell you how we can start working on this. So let's see. The pre-order traversal is this. So what can we read from this? So I'm claiming the root is, what's the root? The root is 6 because, looking at pre-order, the root is 6. So what I'm going to do, I will show you my amazing PowerPoint abilities. Yep, the root is 6. That's good. Okay, so if the root is 6, can we get what's on the left and what's on the right? So if you look at in order, this will be on the left and this will be on the right? Because that's exactly how in order works, which means here, this is on the right. Sorry, this is on the right and 4, 7 are on the left, right? And then so the left subtree will have 4, 7 and right subtree has 8, 2, 1, 9. Okay, so let's do the left subtree first. All right, so we have 4, 7. The question, which of them is the root and which of them is a child, and is it a left child or a right child? Okay, so the left, let me say it again. The pre-order is 4, 7. So if pre-order is 4, 7, well, it means that we have 4 here, and 7 is the child. Right? So for now, I don't know if it's a left child or right child, but I definitely know that 4 is the root of the left subtree. Now, is 7 the left child or the right child? That's the question. But let's look at the in order. So for the in order of the left subtree, we have 7, 4. 4 is the root. Does it mean that 7 is on the left or on the right? So in order says left, root, right. Well, there's nothing on the right. There's only root and something on the left, which means that 7 is on the left. Okay, so 4 is the root. So now let's process the right subtree. So for the right subtree, who is the right child of 6? So who is the, on top of the left subtree? Well, in the pre-order traversal, 8 comes first, which means that 8 is the root. Right. And what about this 219? How do we decide who's on the left, who's on the right? Well, we do the thing recursively. 8 is the root. Everything here is on the left, everything here is on the right. So who's on the left of 8? Yeah, it's 2. And who is on the right of 8? On the right of 8 is 9 and 1, right? So 2 is on the left and 1, 9 are on the right. But which one of them will be, above the other? Is it 1, 9 or 9, 1? Let's see. In pre-order, it comes as 1, 9, right? So this is the entire thing. Right, so here and uh, in order is 2891. So 8 is the root, 2 is on the left, 9, 1 is on the right. So it means 9 and 1 are on the right of 8. And their pre-order is 1, 9, which means 1 comes first. What about 9? Is it on the left or on the right? So for in order, it's 9, 1, nothing. No, 1 is the root of this little subtree, which means that 9 will live exactly here. And let me connect the rest of the lines. Okay, so in pre-order, we have 1, 9, meaning 1 is the root. And in order, we have 9, 1, which means 9 is on the left. Okay, so that's the tree that we got. Okay, I hope you got this example. Actually, in the lab assignment, you will actually need to write code, that gets two traversals, pre-order and in-order or something similar, and you need to um, reconstruct the tree from it. Right. Let me say something a bit more general. So here are mm, some facts. You can reconstruct a tree from okay, pre-order and in order. You can also reconstruct a tree from post order and in order. But you cannot reconstruct a tree only from pre-order and post-order. Okay, and here find an example. So here's an exercise for you. Exercise, find a counterexample. Namely, find two different trees that have exactly the same post order and in order. Find two different trees with same pre-order and post order. Right, so if you find two trees with exactly the same pre-order and post order, it means that well, you cannot reconstruct the tree uniquely. Okay, that's your exercise. Okay, now let's go to the next question. And the next question is the following. I feel it's maybe easier. So write a function that gets two vertices in a binary tree. So let's call them u and v, and decides if u lives under v, if u is a descendant of v, namely u may be a child of, okay, let's say equal to v, a child of v, a grandchild of v, or grand-grandchild. And note that we don't know if we need to go right or left, okay, in each step. So if u lives under v, so how would you do that? Right, so we get two pointers, a pointer to u, a pointer to v, and we need to decide. So, think about it. If you start from V and you try going down, you sort of need to do all possible, you probably need to do one of the traversals and see if you see U, but there's a faster way to do it. Namely, you start from U. And you start from U, and, we call it P, so it will be like a pointer. And, well, if U is equal to V, yeah, then we say, yeah, U is a descendant of V, maybe in some degenerate sense. Right. But U is lives in the subtree of V. And if not, let's start from U and try to go one step up. And if we see V, then we say, oh yeah, U lives under V. If not, we'll go one more step up and one more and one more and one more. So the loop is we start from P equals U and we go up and we go up and we go up. And if at some point we see V, then we return true. And if we reach the root and then jump out, then we return false. That's your algorithm. Uh, Let me ask you, what's the running time of this algorithm? So here's the running time. So if U lives really under V, if U is a descendant of V, then the running time is effectively the distance between U and V, right? So if U and V are really close, then, maybe two steps, then this will have two steps in this iteration. So it's really fast when U is close to V. And in general, if U is not under V, then the running time, will start from U and go up until we reach the root and then we exit. So it's the depth of U. That's the running time. So if our tree is kind of balanced, then this algorithm is maybe efficient. But if the tree is kind of a long string and U is at the bottom, so we'll need to make many steps. Okay, and your exercise is to implement this, but let me make it easier for you and I will implement this myself. So okay, I will not do exactly that. What I will do is compute list of ancestors. So given a node, in this case U, or I call it node, I'm going to create the list of all ancestors, and then we need to only check if V belongs to the list, right? So it's kind of a related problem. But I suggest you still implement this because it's kind of easier than what I'm doing. So here's what we're going to do. We're going to have a linked list. And let me show you what this linked list. So it's a linked list where data is not a number, but it will be, any type. And specifically the type will be vertices in the tree. So we create a linked list and we set current to be the node. And we say in each iteration, add current to the list. So list add to head current and go one step up. So, we start from a node, we add it to the list, we go up. We add this to the list, we go up. We added this to the list, we go up. So we put inside the entire node, right? Not only the data, but the entire pointer to the node. That's what we put there. All right. And let's see how this part works. So for example, here's what we'll have. So recall this is my list, this is my tree, and I will ask for a list of ancestors of 7. So it will be, 7, 6, 3, 1. So I will call L, L will be the list of ancestors of 7. I'm going to print the value 7, and then I'm going to print the list of ancestors and print, well, we'll see in a second how it works. It's almost what you expect. There is a small trick there. So when we run it, list of ancestors of 7 is 1, 3, 6, 7. I hope that's exactly what we need. So 1, 3, 6, 7. Yeah, that's what we're getting. And if you look at print, so there is this print value. So why do we need this print value? The reason is, recall that our linked list contains data of a generic type. So if it contains data of a generic type, it means it doesn't know that it needs to print numbers, right? What did we put into our linked list? We put inside, nodes of the tree, right? We put inside vertices of the tree. So what linked list print really does, so it gets a list, and it also gets a function that allows us to print, each element in the that we put into the list. So we apply this print data on, one vertex in the tree. Yeah, and then we write a space between them. Okay, and then we go to the next node. So this is your print, except that it doesn't print an int, but rather it prints using a function pointer. You remember we had this function pointer that says, oh, if you have a generic type, you can use function pointer to print a generic data. So in this case, we use this function called print value. And what print value does, it takes a node, which is initially void pointer, it casts it into BT node, and then prints the value. Okay, so in terms of logic, it's just we go over the list one by one and we print the value. But in terms of types, right, L contains nodes, and we need to somehow specify, oh no, from each node you need to extract the data. And print value, that's what it does. It extracts the data. So it prints 1, 3, 6, 7, so which is exactly the list of ancestors of 7. So this was, this exercise. So not exactly is descendant, but related one, print list of ancestors. Right. And the last exercise we'll do for today, I think this is the last one. Oh no, we'll have two more. Good, 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 good. One is called compute distance. So here's another exercise. You get two vertices in the tree, and your goal is to compute the distance between them. So for example, what's the distance between 0 and 1? So, 1, 2, 3, 4. So we go this way. Okay. What's the distance between 15 and 11? Yeah, it's this. What's the distance between 1 and 6? So we need to go up, and then we need to go down. What's the distance between 1 and 25? So we need to go up, and then we need to go down. So I think it's 1, 2, 3, 4, 5, 6. And what's the distance between 6 and 6? Well, it's 0. That's easy. And what's the distance between 1 and 57? So the distance is 4. 1, 2, 3, 4. Okay, so I think in the picture you understand what needs to be done. You need to compute the distance, and the question is, how do you actually do it? Right, so write a function that gets two vertices and computes the distance between them. And sort of, if one is the child of if one is descendant of the other, then it's sort of easy. You need to compute how many steps you need to go up. Right? For example, if 15 is the descendant of 5, then you start from 15, you go up until you hit 5, and the number of steps that you made, this is your distance. Except that when you get U and V, you don't know if one is descendant of the other, or it's the other way around, and maybe none of them is descendant of the other. So how do we do it? Here's an idea. We'll take U and we'll compute the path from U all the way to the root. Then we'll take v. No, well, u and v are kind of symmetric, and we'll compute the path of v to the root. And then we'll find common ancestors, and we'll subtract the common ancestors, and we'll see how it goes. So here's an example. So let's say we have 25 here and 6 here. So what's the path of 25? It's this path. What's the path of 6? It's 6, 15, 11, 5, 0. This. So we need to do 1, 2, 3, 4 here and 1, 2 here. So together it's 6. Right. So it's 1, 2, 3, 4, 1, 2, together that's 6. Let's try another example. What about 1 and 57? So for 1, we need to go all the way up. So 1, 15, 11, 5, 0. For 57, we need to go, 57, 5, 0. And do we need to take just the sum of these two paths? Well, no, because they have this, 0, 5 are in common. So what we'll need to do is take the path from u to the root, the path from v to the root, and subtract the common part. Let's try 1, 6. So for 1, this is the path. 1, 15, 11, 5, 0. For 6, this is the common path. And we need to subtract almost all of this. Right? When you subtract all these subpaths. So it turns out the algorithm is the following. Compute the path of u, compute the path of v, count the number of common ancestors, and return the length of the path from u, the length of the path of v, minus twice the number of common ancestors. So, this is what it works out. So if you have 4 common ancestors, 1, 2, 3, 4, you just subtract 8, and then you get exactly 1, 2. And what's the running time of this? So the running time of this is, well, look, there is some work done here. The work of this is the depth of u. There is some work done in step 2. This is the depth of v. Counting the number of common ancestors, you have 2 lists. And how do you count the number of common ancestors? They will both have the root in common. And then you check the next vertex and the next vertex and see how many of them are the same. And so the running time of this is no more than this, the size of these 2 lists. And then we do some, this plus this minus that. So the total running time is the depth u plus the depth v. So order of that. Okay, I hope this algorithm was kind of clear. Okay, so the idea is you start from a vertex and you go up to the root. You start from the second vertex, you go up to the root. If you simply take, right, so what's the length of this path? So it's 1, 2, 3. So if I count it as the number of vertices, it's 1, 2, 3, 4, 5, which kind of corresponds to only length 4, really. Right, so then this number of vertices is plus 1 compared to the number of edges. And same thing here, so we have 3 vertices, so it means 2 edges, but then we need to subtract the common edges. And it turns out that we subtract twice the number of common ancestors, and that works out exactly how we want. And I even have a code for this. And it's not particularly terrible, but though I can't say it's very straightforward. So here's what we do. We take the list of ancestors of L1, take the list of ancestors of L2, of N2. So we get these 2 nodes and we compute the list of ancestors of one of them and the other. And we say as long as, what we see is exactly the same ancestor, we are going to increase by 1 the number of common nodes and go to the next. So we have these 2 lists, and so in this case, the two lists are, 0, 5, 11, 15, 1, and 0, 5, 57. So we'll have this in common and then this in common. So 0 will be the same and 5 will be the same. So as long as we have the same, yeah, as long as we have ancestor 1 is equal to ancestor 2, we increase the number of common things and move to the next thing in the list. And then we just, take the two lists, compute their size, and subtract the two twice the number of common vertices. So let's see if this actually works. If this actually works, that will be amazing. Okay, so we want to compute the distance between 5 and 7. So we go from 5 up, so the ancestors are 5, 2, 1. We go from 7 up, 7, 6, 3, 1. What are the common ancestors? Well, the common ancestors is only 1, which means, we have 1, 2, 3, 4, 5, so the distance is exactly 5. On the other hand, yeah, I don't know what else should we compute. Anyway, try to play with this example a bit more. My point is, if I get rid of print, then, and get rid of comments, the code is not too terrible. So we get the list of ancestors of the two things, and then we traverse two lists at the same time, checking if they have exactly the same common ancestors. And in fact, I suspect we don't need to check the data because we can actually check that the ancestors are the same. But if that doesn't work, that still works. Yeah, we need to compare really that the ancestors are the same. There's no need to check, to check the data. In fact, checking the data is probably incorrect because it could be that, you know, two vertices have the same value, although these are different nodes. So this is actually the correct way to do it. Right? So we check if we have the same node in both lists, we increase the number of common things and make progress in the first list and make progress in the second list. Right. And in the end, be nice and release both lists because we don't need them. We simply need to return the distance. Okay, so this is about computing the distance between two vertices. I hope this is clear. Right, so the last exercise for today is called breadth first search. And let me go back to tree traversal, specifically to pre-order. And here's what I would like to do. So I kind of did it in the past. In class, I would like to do it again. We said that every algorithm that's recursive can be written non-recursively, right? Using a stack. Because this is what's happening really in our computers. There's no recursion there for real. It's just using a stack. So here's what we're going to do. We're going to use a stack. And it will be a stack of vertices of the tree. And essentially, what we're going to do, the stack is going to remember which nodes we want to process. So here's the idea. Here's the algorithm. So we create a new stack and we push the root onto the stack. So basically, root is something we need to process. And then as long as stack is not empty, take a node from the stack, print it, and push its two children onto the stack. Okay, so process the node, remove it from take a node from the stack, process it, namely print, and then add the two children. So now what you need to do is process the children. So your vertex has already been printed. Now you add to your to-do list the children of this vertex. This is what you need to print now. Let me try to give an example, maybe. And okay, so one thing I should emphasize is, we usually process things left to right, but when we push things onto the stack, I first push the right node, and then first I push the right child and then the left child. And the reason for that will be seen in a second. So let's see. How do we, what happens on this tree? So we first push the root, we push 10 onto the stack. We print 10. Whatever's on top, we remove it, we print it, and we add the two children. So, and what's the order? First the right child, 21, and then 5. Why did we put it in the reverse order? Because we're going to remove from the stack actually the left child, right? Because the order is whoever went in last will go out first. So we're going to print 5 and put the children. So the children are 7 and 1 and 7. So we put it in the reverse order so that next we print 1. So when we print 1, 1 has no children, so we don't do anything. 7 has no children, we don't do anything. Now we process 21. When we process 21, we remove it from the stack, we print it, and we add the two children, namely 25 and 16. Why? Because then we're going to print 16, and then we're going to print 25. So the tops of the stack is what's removed in each iteration and printed. So the printing will be 10, 5, 1, 7, 21, 16, 25, which is exactly the pre-order of the tree that we wanted. Okay, so this is your algorithm that uses no recursion and prints, processes the tree in this pre-order. Here is an exercise for you. Implement this algorithm in C. Write code. I don't think I have a code for this. I don't, and it's a very good thing. So you should write the code yourself. Okay, so this is what happens to the stack in all the iterations of this algorithm when running on this tree. So each time we remove the top, for example, if this is our state, we remove 5, print it, and then add the children. And then our to-do list is 1, 7, 21, and the order is, we're going to process 1 first, and if 1 has children, all the children of 1, and then we'll move to 7. Okay, so this is exactly pre-order, right? So we first put 10, again, we put 10, and then we put right child and left child. So until we're done processing all the subtree of the left child of 5, we'll not reach 21. Right? 21 will only be reached after we processed 5 and everything we add, after 5, namely the children 1 and 7. And then we process 21. So in processing 21, we'll add the children of 21, in the right order. And then we process 16 and then 25. Okay, I hope this algorithm is clear. Now, here's a question for you. So, right, one thing, write a code for this. And two, what happens when we replace a stack with a queue? Yeah, I'll count to 5, you think about it. And 1, 2, 3, 4, 5. Okay. So, I'm writing exactly the same algorithm, except that now I use a queue and not a stack. So this algorithm is called, when we simply replace a stack with a queue, the algorithm is called breadth first search. And here is how it works. So we start with, adding 10, adding the root, which is 10, to the queue. Then what do we do in each iteration? We remove 10 and add the two children, 5, 21. And let's say we add it left to right, because in queue, they're processed in the order that they entered. So we first put the left child and then the right child. So we put 5 and then 21. Okay. Then we remove 5. And what do we add? We add the children of 5, which is 1 and 7. Then we remove 21. We remove 21, and what are we adding? 16, 25. Yes, the children of 21. And then, if 1 had more children, we would have added more children to the queue. But since 1 doesn't have anything, we just remove one by one all these nodes from the queue, right? So they don't have any more children. But if they had more children, they would be added to the queue, and we would add more and more of them to the queue until well, we exhaust all the nodes. Okay. One thing, implement this algorithm. But Here is a question. So what's the order here? Okay, so this is my question. Can you tell me what's the order of this traversal, right? So we clearly visit all the nodes. No, we start with the root, and then we put the children, and then the children of the children. So every node will be eventually visited because, for every node, eventually the parent will be visited, and then the node will be. So the answer is we process the nodes layer by layer. So we first put the root, this is 10. Then we put the first layer, those at distance 1. So this is 5 and 21. What happens when we remove both 5 and 21? Look, for 5, we added its children. For 21, we added the children of 21. So after both 5 and 21 are removed, what is left is exactly the second layer. If we have more layers, we'll remove the second layer, and what will be left in the queue is the third layer. And after the third layer, if we remove it, it will be a fourth layer and fifth layer and so on. So it's called breadth-first search because it sort of does this by, well, breadth. Yeah, I don't know. Basically, it traverses the tree layer by layer. First the root, then those distance 1 from the tree, from the root, then those distance 2 from the root, then those distance 3 from the root, and those distance 4 from the root. That's your algorithm, which is, I think it's kind of nice. And it came from this question of, oh, let's implement pre-order without recursion. So, we said, let's use a stack. And then, oh, what if we replace a stack with a queue? And we replaced the stack with a queue. And what we got another traversal, namely this breadth-first search traversal, where we process the nodes layer by layer. Uh, yeah, so this is from Old Things. So I will tell you, these algorithms are this breadth-first search and a bunch of other, they're kind of related to, they have some nice applications. So one of them is this exploring unknown territories, and they're also related to solving puzzles. So in 225, I usually give some examples. So for example, this term, the students will write a solver for Rubik's Cube, and the basic idea is to use something like, one of these search algorithms. But again, this is jumping a bit forward. For now, I hope you just understand this breadth first search algorithm. What can I tell you? Try more examples, okay? Take more trees and try to write more examples and kind of see what's happening. Okay, so do this step by step debugging of the algorithm to see what's processed, what's being printed in each step. Okay, that's all I have for today. Thank you all, and we're done.